What we're going to have a look at in the next couple of videos is a different way of doing local interpolations. And these are based on a technique known as splines. So we've seen that if we use a global interpolation, it can result in large systems to solve. In other words, we might need to invert a matrix that's of order n cubed. Very high order polynomials that can give unrealistic oscillations in the interpolation function. One of the things that we didn't touch on, but is actually the case, one of the benefits of global interpolation is that our interpolating function has continuous derivatives, and sometimes that's important. Now, local interpolation, as we looked at with Neville's method, is generally less expensive. It does provide some kind of error estimate, but it provides us with an interpolating function that is not necessarily continuous in its derivatives. So as we move across from different sets of nodes, we may find that the derivatives change quite drastically, but at least not continuously. So the question is, how can we approach this if continuous derivatives are important for the application that we're looking at? So I'm going to introduce this concept of piecewise continuous functions, and in particular, piecewise continuous functions that are known as splines. And so splines are a set of piecewise continuous functions, but exactly what does that mean? Well, let's take a set of data points, x1 through xn, and between the first two pair of points, x1, y1, x2, y2, we fit a function, f1, which is a function of x. That gives us the y value as a function of x. Between the second pair of points, we fit another function, f2, and these are completely different functions. Between point 3 and point 4, we fit another function, f3, and on we go until eventually we fit the final function, fn minus 1, that goes between points n minus 1 and n. Two adjacent portions of the curve, y is equal to fk of x and y is equal to fk plus 1, pass through a common point, and these points are often called knots. So if we consider the point at xk, that function there is fk, this function here is fk plus 1, and both of these functions have the same function value when x is equal to xk. Likewise, at point 2, f1 and f2 have the same function value. The point at x3, f2 and f3 have the same function value, etc. So that's what we mean by piecewise continuous. So this set of functions, the fk's, forms a piecewise polynomial curve, and we're going to call that curve s of x, s for spline. Even though these splines are continuous at each of the knot points, we don't know anything about the derivatives. So what kinds of spline interpolation can we do? Well, the most obvious one is a linear spline, a first order spline. So we just draw a straight line between each pair of points. So adjacent functions, fi of x, fi plus 1 of x, are equal at that knot point that sits between them. The derivatives are not continuous. The derivatives are quite clearly discontinuous for this particular case. Each of these functions has two parameters. So fi of x is going to look something like ai plus bix. And for each of these functions there will be an ai and a bi. The next thing we could do is we could fit second order splines. So adjacent functions are fj of x and fj plus 1 of x. They match at this particular node point here, but also their first derivatives are equal at this point here. Each one of these functions has three parameters. So fj might equal, for example, ajx squared plus bjx plus cj. Okay, so they're quadratic functions. What we're going to look at in this unit are cubic splines, where adjacent functions fk and fk plus 1 obviously match at this point here, but so do their first and second derivatives. And each one of these functions has four parameters, just like a cubic needs to. So it'll be something like ak x cubed plus bk x squared plus ckx plus dk. Where might we use splines? Why? Well, a really good example is in computer-aided design, also in computer graphics, where we use spline functions, multi-dimensional spline functions, to fit surfaces. So, for example, in this CAD drawing of this Audi motor vehicle here, splines have been used to fit the skin of the car. In digital image software, often uses bicubic splines to look at digital image interpolation. So this is what is used in digital zoom. So if we actually have our original image here and we were to zoom in using an optical zoom, we could see that this image looks fairly sharp. If, however, we use a digital zoom, what happens is that the data in this image here is interpolated to the points in between using some kind of cubic spline. So it gives us a reasonably smooth solution, but it's not necessarily an accurate one. So we're going to spend a little bit of time going through looking at how to derive the equations for one-dimensional cubic splines.